All right, so let's get started on this next section. It'll be short, fast, super easy as well. It still deals with derivatives, but instead of us doing that big formula like, the limit as h approaches 0 of f of x plus h minus f of x over h, we're going to be talking about basically rules for derivatives or how to find them, and it's super fast and super easy. So that old stuff that we did from chapter 2, it's not going to come up again. Or as far as finding that derivative via those methods from chapter 2, that's not going to come up until the final. So now it's going to be pretty straightforward. And I know a lot of people are going to be thinking, well, why didn't we just go over this quick way first, right? Well, it's all about learning where things come from, right? So 3.1 is the derivative of polynomials. What else are we deriving right here? And exponential functions. So, as far as these rules, what are they? Okay, so if we recall, like if we have, I'm going to say notation for derivatives. So remember, if we have like the first derivative, we talked about it a couple days ago. You could have like y prime, we could have f prime of x, for example, like that. Another one that I'm going to introduce is something called ddx of a function, or really it can be anything. So when I say anything, it could be a number, a polynomial, exponential function, trig function, whatever, log function, any of that stuff. So when you see this ddx, that means first derivative, okay? Like if you saw something denoting a second derivative, we also have y prime prime or f prime prime of x. And this third form right here, this ddx, it also exists as well as a second derivative, like d squared over dx squared, like that of anything, or whatever it is you're taking the second derivative of. And then if this was like a 3 and dx3, it'd be third derivative, or y prime prime prime, third derivative, and so on, like that. Now, as far as the rules, or the basic rules that we're going to look at first, well, let's say we have, and I'm going to use ddx, okay? What that means is you are taking the derivative with respect to x. So for those of you who take multivariable calculus, you'll actually do something called partial derivatives, where this could be dy or ddz. So that means you would take the derivative with respect to the y variable or the z variable or whatever variable you're looking at. But all the rules still work the same way. It doesn't matter if we're talking about x, y, z, or whatever letter of the alphabet, they all work the same way. So if we were to look at ddx of c, so c is a constant, okay? Well, ddx of any constant, that's just a number by itself, okay? It's just equal to 0. Doesn't matter if I have ddx of 10, ddx of e to the fifth power, it's still 0. Why is that? Well, if we think about it conceptually, all right, like let's just say I have y equals 5, right? That's a constant right there. It's not 5x. There's no x within this equation right here. If we were to graph this thing, this is a horizontal line at 5. This is a horizontal line. Remember, what does derivative mean? It means the instantaneous rate of change, a fancy form of slope, right? Just fancy phrase for slope. What's the slope of any horizontal line? It's a line that runs from left to right. It's not rising at all. It has zero rise, but it is running, but that's always equal to zero. So the slope of any horizontal line running left to right is always going to be zero. But what's the only type of thing or numbers or whatever expressions that can give horizontal lines? It's y equaling to some constant only. So again, it doesn't matter what this number is. All right, the slope or derivative of that specific constant will always be zero. So if I have d dx of and your expression is 8, that's equal to zero. Doesn't matter. Or if I have d dx of the square root of 98 is still zero. Why? Because it's just a constant. A constant is a number. Don't get tripped out and say, oh, there's other stuff in here. If I have d dx of e to the ninth power, like that. Remember, e is a number, right? It's approximately equal to 2.71. That's still a constant, so the derivative is zero. So these are super easy. There's nothing to do. You just have to remember, oh yeah, it's zero. Now, what about the most important rule for these derivatives is something called the power rule. So let's say we have d dx of x to the nth power, some power of n. So now we have an x, right? We no longer just have a constant by itself. Now the way you derive these is it's going to be n times x to the n minus 1 power, like that. So basically, you're shoving the exponent down here, the x stays the same, and so you're subtracting 1 from that exponent that's in the, that you're subtracting 1 from that n that's part of the exponent. And that's all that there is to it, okay? So, like, if we had, say, y equals x to the 5th power, and we wanted to find d dx of this. So how do we do that? Well, what's your n in this case? Well, if we look at the power rule, right, just following this, n's 5. So we get dy dx. This also signifies first derivative as well. The derivative of y with respect to x. That's how we look at that. So if we look at this, n's 5, what do you have to do to take the derivative? You bring down that 5. 5 times x to the n minus 1, or 5 minus 1 power. That's just equal to 5x to the 4th. There's your derivative right there. You don't have to write this 5 minus 1 step if you don't want to, because we all know, yeah, 5 minus 1 is 4. But you can't have fractional exponents, right? So it might help to leave that minus 1 up there so you can visualize it. But that's all that there is to it. We actually could have used that formal definition. We could have used, this thing right here. We could have applied this formula to this equation right here, and we could have solved it, and we would have ultimately gotten this. But that would have taken a lot of time, right? Remember, it was very tedious. But look how fast we were able to do it right now. So this is a great rule right here. It's the one you're going to use the most. So yes, you have to commit these rules to memory, but you're going to work like 1,000 of these problems because they're just that easy right there. Just watch the signs, watch the arithmetic with these right here. Like, what if you have y equals, say, x to the negative 2 power, for example? So of course, you can have negative exponents, right? When you derive or take the derivative of functions, this shouldn't be an issue. Why? Because we can follow the power rule, right? Look at it. So if we take d dx of both sides, right? Because that's what we're trying to find out right here. How do we do that? Just follow the power rule. right here. So what's our n in this case? Negative 2. What do we have to do with that? Bring it down. Negative 2. X to the negative 2 minus 1. This is a spot where a lot of people are going to mess up because they're going to go negative 2 plus 1 or 2 minus 1. And no, that's not it. It's negative 2 minus 1. So your derivative is negative 2x to the negative third power, right? Be careful with that arithmetic. I know some people are going to say negative 2 minus 1 is negative 1 or 1. It's not. It's negative 3. So watch the arithmetic with these right here. That's what gets people with this. What if I had y equals x to the 3/4 power? Something like that. Well, if we want to try to find the first derivative, how do we do that right there? Well, again, follow the power rule. Remember, it becomes n times x to the n minus 1 power. So this becomes 3/4, right? Because that's the n. X to the 3/4 minus 1. Well, you got to simplify, right? This is still 3/4. This is x. But what's 3/4 minus 1? That's negative 1/4, right? So again, just watch the arithmetic right there. That's the spot that people mess up on. Just subtracting or adding up the numbers that appear in there like that. Now, what if you have something like this? It's y equals uh, I'll say the fifth root of x, something like that. Fifth root. That's not 5 times square root of x. Fifth root, that's the index, right? That's the type of root we're dealing with. How do we find its derivative right here? Well, anytime you have radicals, whether you're finding the derivative or later on when we're finding the antiderivative, what we should do is convert them into exponential form, okay? Because then once you do that, you can apply the power rule. Remember, if you have, I'll say the nth root of x to the mth power, so that you could have exponents inside, right? This becomes x to the m over n. Remember that. This is something from algebra that you should know right here. So the denominator of your exponent is the index. Whatever this exponent was, that becomes the numerator of that fractional exponent, okay? Very important to remember that right there. X to the m over n. So this, in reality, is x to the 1/5 power. 5, again, is the index. This 1 from the numerator, where's that coming from? Because, remember, there's an imaginary 1 right here, right? If they don't have something, it's just 1. So we have that. But we're not finished, right? We're trying to take the derivative. So dy dx, so we're taking d dx at both sides. What would that be in this instance? Same thing like what we did for this problem here. Same exact thing. Now, power rule time. So you're going to drop the fifth. And then we're going to have x to the 1/5 minus 1. You got to simplify that though, right? 1/5 minus 1 is negative 4/5. Don't sit here and keep multiplying this exponent into that. Don't keep doing all that stuff. We're just finding the first derivative. What if we had y equals the square root of x cubed now? So again, we need to convert this into exponential form. We have that formula right there. If they don't give you an index, right, they leave it empty, it's not nothing. By default, it's 2, right? So if you need to, throw in a 2 right there. So let's rewrite this in exponential form. This is x to the 3/2. Now we get to apply the power rule, right? dx of both sides. So what do? We have dy dx equals, well, bring that exponent down, 3 halves, x to the 3 halves minus 1. We can continue to simplify this, right? This is 3 halves x to the 1/2 power. So yes, you need to combine your fractions. All right, combine those numbers into one number. It can become positive or negative, right? It depends on just what you initially started with. Now, what if we had something like this, like y equals 1 over x to the 8th power? 8, 8, 8. So remember, all we know is the power rule, and that's about it, right? And the derivative of a constant. Well, we can't use the power rule on this just yet because it's not in that form x to something. It's 1 over x to some power. So we have to manipulate it a little bit. So we need to somehow get this x to the 8th to the top. Well, we can do that, right? Remember negative exponents? Like if I rewrite this as 1x to the negative 8th, these two are equivalent, right? Because remember, if you have a negative exponent, you can flip whatever that negative exponent is being applied to, right? So you can flip this down and get back to this. So this is what we're working with right now. So now we can go ahead and take the derivative. So again, power rule, right? This becomes negative 8, x to negative 8 minus 1. Watch the signs, right? Negative 8 minus 1, that's negative 9. There you go. That's your derivative. So if you have fractions where your x is in the denominator, you just bring them up by making the exponent negative, and then you can derive it from there. Now, what if we have, say, something like this, like y equals 5x to the 3rd power, something like that. Now we have something other than 1, right? Or just x by itself, we have something in front. If you have something in front, you still derive it the same way. It's just that you're going to multiply whatever is in front times that n that you drop down. So when you take this derivative, we're going to have 5 and then times 3 to the x, or 3 times x to the 3 minus 1 power. So we're just multiplying, okay? So then you wind up with 15x squared, and that's all there is to it. If you want, you could jump from here to here, okay? You say, oh yeah, 3 times 5 is 15, 3 minus 1 is 2, boom. That's totally fine, but starting out, you should write this out so that you can commit or see visually what's going on, because a lot of people go from here to here and they start making mistakes. They multiply something incorrectly or subtract a 1 incorrectly. All right, so now we have y equals 5/6 times x to the 2/3. This is an exponential form, right? So we're good to go. We can apply the power rule. So dy dx, if we take the derivative of both sides with respect to x, how are we going to do that? It's the same way, right? We're going to multiply these two powers together. We need to drop this down. So this is 5/6 times 2/3 x to the 2/3 minus 1. And then we multiply, right? With these fractions, we can reduce them partially, right? Like 2 goes into 2 once and into 6 3 times. That's definitely possible. You actually have to reduce if possible, right? So now we have 5/9, and then x to the negative 1/3 power. Don't fear these fractions, like doing 2/3 minus 1, for example. That stuff is very common. So if you're not good with fractions, practice them because you're going to get them a lot while doing these. Now, what if we have more than one term, right? Because so far we've only been deriving one thing, like one. This is all one term right here. What if we have, this plus or minus a bunch of other things? Well, we have this thing called the sum and difference rule. Basically, it says, oh, if I'm taking the derivative of plus a bunch of different functions. So I have f of x plus g of x plus dot dot dot. That just means like you'd have h of x, z of x, whatever. It doesn't matter how many things you're adding or subtracting. Then what you simply do is you derive each piece individually. So we'd have d dx of f of x plus or minus d dx of g of x plus dot 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 and so on. So you just take, work each little piece individually and then combine like terms if you can. So like if we had, y equals 9x squared plus 4x to the sixth minus 3x, like that, plus 5. There we go, like that. And you want to find the derivative. Well, if we did that, well, we would apply this d dx to every single term right here. There's 4 terms. So do you have to write out this d dx for every single piece? No, you could just say dy dx and then derive it straight through. That's completely fine right there. So let's start that. So if we take the derivative of 9x squared, remember it's all power rule stuff. You go 2 times 9, that's the exponent, right? The exponent is 2. So we get 18x to the, we have 2 minus 1 power. And yes, we will simplify that. Now, if we move on to the next piece, if we apply the power rule, we need to drop the 6 down in front. But there's a 4 there. So you multiply, right? 6 times 4 is 24. X to the 6 minus 1 power. This one right here, remember there's a 1, right? If they don't tell you anything, there's a 1. That's 3x to the first. So we go 3 times 1, right? That's just 3. And then we have x to the 1 minus 1. Kind of weird. We'll get to that in a second. And then plus d dx of 5. Remember, there's a constant. Derivative of any constant is 0. Did you have to write the 0? No, because it's just 0. If we continue simplifying, we get 8x to the first, right? You don't have to put the 1. You could just put 8x. This is 24x to the fifth. This is minus 3x to the 0th power. Now remember, if you have, I'll put an asterisk or whatever, x to the 0, remember anything to the 0 power that exists is always what? It's always 1. So this actually becomes 3 times 1 right here. But that's just 3. So your final answer is just 18x plus 24x to the fifth minus 3, like that. So don't forget, derivatives of constants are always 0, right? And the rest of them, if they have some kind of exponent, they follow the power rule. In this case, they didn't give us an exponent, but it's understood to be a 1. So if you need to, put a little 1 right there. All right, so now we have 2x minus root x. And again, we're just trying to find the derivative right there. There's two pieces, right? So we don't have 4 like last time. We're still going to do it the same way by applying the power rule. Remember, if you have a root, which you do right here, you need to convert that into exponential form. So let's do that. This is still 2x, so this becomes minus x to the 1/2 power. Where did I get that 2 from? Remember, if they don't give you anything right here for the index, that's 2. This 1 comes from it being x to the first, like that. That's where we're getting that from. So now we can apply our derivative with respect to x for these two terms. Remember, there's 2x to the first, right? If you need to put the 1, that's fine. So we do the power rule again. You go 1 times 2, right? 1 times 2 is 2, and then we have x to the n minus 1 power, or 1 minus 1. This next term, there is technically something in front of this, right? There's a 1 right there if you want to put something right there. So we do the power rule again. 1/2 times 1 is a half. And then x to the n minus 1 power, or 1/2 minus 1. And then we simplify, right? We get, this is 2x to the 0. Well, we already saw what happened with x to the 0. That became 1, right? So this will become 2 in the end. This is 1/2. And then x to the negative 1/2 right here. So you're left with 2 minus 1/2 x to the negative 1/2 power. That is your derivative. All right, so now let's try this. Like, we want to find an equation of the tangent line at the point. So remember, we did this in chapter 2, right? We were finding an equation of the tangent line at a given point. Remember, you needed two things, right? A slope and the point. And to find the slope, we had to do that whole limit as, x approaches a, blah, blah, blah. We don't have to do that anymore. We can just find the derivative using the power rule, and that's going to give us the generic slope equation for any point on the curve. So remember, slope, m is equal to dy dx, right? But can we use the power rule on this currently, how it's written out? No. So you need to write this out in exponential form. The cube root of x written in terms of exponents is x to the 1/3 power. Remember, the index is the denominator of your fraction. Now, if we take the derivative, remember it's still the power rule, it becomes n times x to the n minus 1 power. So this is 1/3 and then x to the 1/3 minus 1. All right. So this is 1/3, and then x to the negative 2/3. So we have our generic slope equation, right? We have our generic slope equation for this curve right here. But remember, we want the equation of a tangent line at one specific instant. It's at the point 8, comma 2. So we need our slope at 8, comma 2. How are we going to get that? Well, we're going to use this x value right here and plug it into this equation, and it's going to give us the slope at x equals 8. Now, you may be thinking, well, what do we do? We have a fractional exponent, and we have a negative fractional exponent. Whenever you're evaluating a function that has negative exponents, you should make them positive first. So if we do that, how do we make a negative exponent positive? We flip it, right? So this becomes actually 1 over 3x to the 2/3 power. We do not flip this 3. Why? Because does this 3 have a negative exponent being applied to it? No, just the x does. So yeah, you always want to convert your negative exponents to positive exponents when you're evaluating a function. So now we have 1 over 3, and then we have this a to the 2/3. So how do we evaluate a to the 2/3? You can plug in your calculator, right, with the caret key. But remember, fractional exponents are the same thing as radicals, right? We were converting from radical form to exponential form just a couple minutes ago. So this is really 1 over 3, and then this is the cubed root of 8 squared, right? I'm just working backwards here. This is not difficult. This is still 1 over 3. But what is the cubed root of 8 squared? Well, what's the cubed root of 8? 2. And then 2 squared is 4. So your slope is actually 1/12. Again, how did I get the 4 from this cube root of 8 squared? Because you can do it two ways. You could say, oh, what's 8 squared? 64. What's the cube root of 64? 4. Or you could do the cube root first. What's the cube root of 8? 2. 2 squared is also 4. So you see, it doesn't matter which way I go. You can take the index first and then square it, or square it first, then take the index. You'll still get 4 in the end, okay? But this is our slope, 1/12 at the point 8, comma 2. So now where do we go from here? Because we want an equation of the tangent line at that point. So we have y minus y1 equals m times x minus x1. So we're going to use this, right? This is our x1 and y1. Let's plug all this stuff in. We have y minus 2 equals 1/12. And then x minus 8. And then we keep going, right? This is y minus 2 equals 1/12. X minus 8 over 12. And yes, we are going to reduce that. I'm going to reduce that on the next line. You should always reduce fractions and roots, right, if possible. So we can add 2 to both sides, right? Do that. Now we have y equals 1/12 x minus 8 over 12. What does that reduce to? 2/3, right? Because they're both divisible by 4 plus 2. And then we can combine these into one term. So we have 1/12 x. Negative 2/3 plus 2. Well, 2, remember, is like saying 6/3. So negative 2/3 plus 6/3 is 4/3. Remember, we're just creating equivalent fractions right here, right? 6/3 is still 2. That's how we know we did that correctly right there. So it's the same steps that we did, from the previous chapter. It's just that it's a little quicker because we know the power rule for the derivatives, right? We know that right there. Now, what if we had a slight variation of this, or a different type of question? So we want to find the points on the curve where the tangent line is horizontal. All right, so what does that mean conceptually? Like, what are we trying to do right there? Well, if we just look at a rough sketch of this thing, okay, I'm just drawing a rough sketch. It's like 7. It pretty much does something kind of like this, or uh, there we go, something like that. So your curve kind of does something like this right here. So what they're asking for is they're saying find the points on the curve where the tangent line is horizontal. So remember, what are horizontal lines? They're lines that run left and right and are flat. So they're talking about with this right here, like that, and right here. They want to know where are these x values where this is happening at right here, or what's the point where it's happening? That's what they want to know. That's what they're trying to figure out right there. So how do we do that? Well, remember, derivatives give us slope, right? What are the slopes of horizontal lines? 0. Slopes of horizontals are 0, right? Because that's what gives us the flat lines. How are we going to find that, though? How can we find the slope for this thing? Well, we can take the derivative, right? So I'll give y'all, like a minute or something. Try to take this derivative right here. So if you want, you put dy dx equals something, y prime, same thing. It still means first derivative. All right, so if we do that, right, power rule for all three of these right here, what do we get? We should get 6x squared minus 1 gives you 2. Minus 6x, remember the 6x to the first. And anytime we had x to the first, that basically disappeared. So we have minus 6. And the derivative of a constant is just 0. So you're left with 6x squared minus 6. Now remember, this just gives us the slope equation for any point along this curve. We're not looking for any point, right? We're looking for a very specific point. We're looking for the points on the curve where the tangent line, this purple and green line, is horizontal. And like we said before, horizontal lines appear when your slope is 0. So what do we need to do with this slope equation? Set it to 0. Or we can say horizontal lines occur when slope, or in this case, when 6x squared minus 6 is equal to 0. So whatever your first derivative is, that's where the horizontal lines occur when you take that first derivative and set it to 0. So now how do we solve that for x, right? How do we do that right there? Well, what can you do? Remember, if you have no idea, ask yourself, can you factor? And you can. We can pull out a 6, right? And in doing so, we're left with x squared minus 1 equals 0. And then from there, what's another step that we can do? You could factor this. This is the difference of two squares. Now this is x plus 1 times x minus 1. So now we can set these to 0, right? We have x plus 1 equals 0. X minus 1 equals 0. Do we need to set this 6 to 0? No, because there's no x in front. There's no x right here. We only set the x stuff to 0. So we could see that we have a horizontal line occurs when x equals negative 1 and x equals positive 1. Remember, that's just us solving, right? You subtract 1 from both sides, you add 1 to both sides. But we're still not finished, right? Because it was asking for the points, the point at which these horizontal lines occur. A point has an x and a y. We only have the x's. So we need to find the y values, right? Got to find the y values of those 2 points right there. We can do that because we have the original equation, right? So at x equals negative 1, y equals, we have 2 times negative 1 cubed minus 6 times negative 1 plus 7, right? And watch the signs. This is plus 6 plus 7. This is negative 1 cubed. Negative 1 times 2 is negative 2. So negative 2 plus 6 is 4 plus 7 is 11. So we have it at negative 1 comma 11 is where we have a horizontal line happening at. We also need to do it for x equals positive 1. So this is just 2 minus 6 plus 7, right? So then we get 3. So your other answer is 1 comma 3. So these would be the answers, right? Because again, they're asking for the point at which the horizontal tangents occur at. Again, that's where the slope is equal to 0. How do we find the slope for these equations? You take the first derivative and you set that derivative equal to 0 and you solve for x. And sometimes you may only get one x value, or you could get 10. It depends on what your initial expression was. Once you get those x values, right, like we got right here, you need to plug them back into the original equation to find the point. Don't plug them back into the derivative because you will always get 0. That's what you solve for. So these numbers that you get, you must always plug back into the original equation. All right, let's try another one. Here's our equation. All right, so looking at this, again, we're trying to find the horizontal lines where they occur at. How do we do that? We take the derivative and set it to 0. So if we do that, power rule, right? This becomes 4x cubed. This one becomes, well, we got 2 times 8, or negative 8 is negative 16. X to the 2 minus 1, which is 1. And then the derivative constant is 0. So remember, this is our derivative, right? We can say this is dy dx, right? And we need to set this to 0, correct? Got to set this thing equal to 0 to get our 2x values, or I'm sorry, 3x values where this is happening at. So in this case, again, if you don't know what to do, ask yourself, is there a GCF? Yeah, there is. There's a 4x. If we take out a 4x, what's remaining? X squared minus 4 equals 0. And you keep asking yourself, can you factor more if possible? Yeah, this is the difference of two squares again. Now we have 4x, and then we have x plus 2. X minus 2 equals 0. So just like the last one, we're going to set this time all three of these equal to 0, right? Like we have 4x equals 0. I'm going to use this one because there's an x next to the 4. And then x plus 2 equals 0. And then x minus 2 equals 0. So if we solve them, right, this becomes x equals 0. This becomes x equals negative 2. And then the last one becomes x equals positive 2. So this is where you will be getting your flat horizontal lines, right, occurring at the humps at x equals 0, negative 2, and 2. But we were being asked what's the points, right? So we got to find their respective y values. So at x equals 0, we have y equals 0 to the 4th minus 8 times 0 squared plus 2. That's equal to 2. So that's at the point 0, 2. Now we have to put in negative 2. So this becomes 16, right? This becomes negative 2 squared is 4 times negative 8 is negative 32 plus 2. So we get 16 minus 32 is negative 16 plus 2 is negative 14. So for this one, it's at negative 2 comma negative 14. And then for the last one, x equals positive 2, you still get 16 minus 32 plus 2, and that gives you negative 14. So this one occurs at 2 comma negative 14. These would be your three answers that you end up with, because again, it's asking for the points where your horizontal tangents are happening at. So again, the process is always the same. You take the derivative, you set it to 0, you solve for x, then you stick those x values back into the original equation to solve for the y's. All right, so now we're going to do two more problems. two more little problems. Like let's say we had y equals x plus 5 squared, and you want, I'll say you want y prime. So we want the first derivative, right? So we only know the derivative of a constant and the derivative of how to do like basic power rule stuff. This is neither of these right here in its current form. There are other ways to learn, like we're going to talk about next class, called the chain rule, and you have the product rule and all that good stuff. But we only know the power rule and the one for the constant right now. So what do we need to do? Multiply. So sometimes you have to multiply or distribute these things out. So in this case right here, this is a FOIL, right? FOIL this thing out. Or like I said before, sometimes you may have to distribute. So if we FOIL, we get x squared plus, it's not just x squared plus 25, right? You have the outer and inner, so you wind up with 10x plus 25. So now we're trying to find y prime, right? I'm going to use y prime right here. Same thing as dy dx. If you want to write it like that, that's fine. So if I go ahead and apply the power rule to all these, what do we get? We get 2x to the first. We get plus 10x to the 1 minus 1, right? So there's a 1 right here. You're going 1 times 10 is 10, and then 1 minus 1 is 1. Like how up here we have 2 minus 1, if you want to write that. And what's the derivative of a constant always? 0. So what does that leave us with? We get 2x plus 10, or 10x to the 0, right? But remember, what is x to the 0th power? That's just 1. So you get 2x plus 10 times 1, and that's just 2x plus 10. Remember that, okay? That x to 0 is 1. That's always going to happen. A shortcut for that is if you have d dx of cx to the first power, where c is a constant, it's always equal to c. Whatever that number is like that, that's what's happening right there. That's always going to happen because of that power rule right there. But just remember this right here. All right, and then the last little thing is derivative of e to the x, or y equals e to the x. This is a very unique function because it's the only function out of all the functions in math at all that have the same derivative and antiderivative, which we're going to get to, like way later on. And it's super easy. So d dx of e to the x is, guess what? Just e to the x. That's it. Nothing else. Okay? Yes, you can have other numbers in here besides 1. Like you could have e to the 5x or e to the sine x. That's something that will derive later on. So if I have, like, say, d dx of, even if I have 3 e to the x, for example, guess what? It's still 3e to the x. All right? But again, yeah, it's a very unique function because, again, it's the only one whose derivative and antiderivative are the same exact thing. No other function in all of math does that right there. So next class, we're going to introduce more rules to derive different types of functions because, like I said before, there's stuff like logs and trig functions, and the rules, they're not as nice as this power rule that we've been doing, right? But make sure y'all practice this right here. There's a bunch of little problems on the web assign. They are unlocked. The due dates are up, and I believe your next test will be falling on Monday the 14th because it's just 4 sections, okay? But this one's a lot easier because it's just these rules that you have to remember. So you will have to remember stuff like this, okay? It's not going to be given to you on a formula sheet. But by then you have worked out some of these problems that it'll probably be fused in your brains, okay? So if you haven't done so, make sure you email me, your scratch work for the from the test. Or you can take a picture with your phone of your loose leaf and then send me an email, okay? All right. So any questions on this right here?
Yes, Mr. Spark, quick question. What is that called? Is there a name for it where it says DDX and you have
This,
CX1? No, up at the top right hand corner.
oh, that would be, if you
Yeah.
want to call that, I mean, it's just like derivative of a constant times x to the first power. There's no like phrase for it. I mean, just what you just need to get from it is that if you have like ddx of say like 8x, it's just 8 like that. Like whatever the number is in front of that x to the first, that's the derivative right there. So
Okay.
yeah,
Thank you.
sure. Any other questions?
What you said about the scratch paper?
Oh, email it to me. Email, take a picture with your phone and then email it to me.
Okay.
Okay. All right. So y'all have a good weekend, and I will see y'all on Monday.